Okay, welcome to everybody to a new session for the seminar of Búsqueda de Nueva Física en Aceleradores y el Cosmos. Today we come with, we have the Professor Georgios Papathanasiou. So let me read a brief presentation about him. So he's a theoretical physics aimed to predict the outcome of elementary particle collisions with the help of contemporary mathematics. He returned to the faculty of UAA Physics Department when he also get his first degree in March 2025. Before that, he worked as senior lecturer at UK City St. George's University of London as a staff scientist of Germany Deutsches Elektronen Synchrotron National Research Center. He also held postdoctoral position at SLAC Stanford, LAP Annecy, as well as at the University of Florida, and he got the PhD from Brown University in 2011. So thank you so much, Professor Georgios. Please go ahead.
Thank you very much for the invitation. Albeit in this time for an online seminar. I've been to Mexico once in person in my life, and I sure hope there will be a second time. So today I'll be talking to you about some work based on this paper together with Dima Ciceri and Johannes Hen, and mainly on more recent work together that builds on it with my current student Riger Saliai, and also with on a paper to appear with my student and my former postdoc Gabdian. So let's start smoothly. I will start with the big questions that motivate my research that also resonate with your department. So the main question of particle physics is to find what the fundamental constituents of matter are and how they interact. And this we do it with collider experiments, such as the Large Hadron Collider at CERN, Geneva. You see this huge ring under the ground. And so in this huge ring, you see a cartoon of it also over here. We accelerate protons almost at the speed of light, and then we have them smash into one another, and we see what comes out. Of course, the protons themselves are not elementary. They have constituents. They have the quarks, which are fermions, matter particles, and then they also have the gluons, the carriers of the strong force that binds them together. And so it's these particles that really interact. And then similarly, these particles will also come out, will be the outcome of the collision. And in this cartoon over here, I have, for example, two gluons coming in from the two protons. And after the collision comes out one more gluon that then loses energy and radiates and converts to other particles that form a narrow cone called the jet. And out comes also a Higgs boson. The Higgs boson, which its discovery was a major breakthrough. It was, discovered in 2012, named after the great British physicist Peter Higgs, that passed away, unfortunately, a year ago. And it was the last missing piece of the puzzle, the particle that gives mass to all the remaining particles, and a major breakthrough for our field. It's, I think, quite fascinating that this particle was theoretically predicted 60 years before its experimental discovery, which is quite amazing how theory can precede experiment sometimes and motivate it. And speaking about the connection between theory and experiment, central to this connection is a quantity called scattering amplitude. This is part of quantum field theory, the theory that brings together quantum mechanics and general relativity and describes all forces in nature but the gravitational force. And it can be very succinctly fit even in a t-shirt. So this object, it really visualizes the scattering event. You have some incoming particles that we knew were moving freely far away, and then they come close, they interact, they talk to each other. This is the region where we don't know what's happening, we're not looking. And then very far, again, from the interaction region, far in the future also, we detect some new free particles, again, P3 to Pn. And then this is, since this is, of course, the quantum world, we can always talk about probability. We cannot know for sure what the outcome is. And this scattering amplitude, which I denote here, cal AN, for the number of particles that participate, the absolute value square gives the probability of this collision, the probability that this particular outcome will come when we all know what were the free particles in the far future, far past. And so, as I said, quantum field theory tells us how to theoretically find this probability, which is important input for experiment. And computing this efficiently is important because it allows us to measure some of the constants that appear, some of the coupling constants, some of the fundamental constants, the numbers that show up in these equations. For example, the coupling of the Higgs field to the fermions that you see over here, these Y's, and this we are in the process of computing, and this will go on in the high luminosity, especially era of the LHC. And apart from really making sure that standard model is the right theory by also measuring these couplings, we of course want to tell subtle departures of the measurements we make from the standard model, which would therefore hint towards new physics, toward phenomena that we have not understood yet. So scattering amplitudes are at the center of particle theory confronting meeting experiment, and their computation is again critical to do. And speaking of the computation, how do we do it? We can never do it exactly. We compute the scattering amplitudes approximately in one of these constants, the coupling constant G, that shows up, let's say, that hides in this first term over here, and it measures how strong the interactions between the particles are. And we have a series expansion with respect to this parameter. So up to an overall factor, yes, the 0th order term, and so on. And so every term in this expansion, thanks to the work of Richard Feynman, we can compute it. We can first visualize it by means of Feynman diagrams that very nicely indeed visualize all the different ways with which quantum particles can interact, and these all different ways we sum them up in the end. And depending on the order of this perturbative expansion, you see that the graphs, so external legs have to do with the particles that we observe in the past or in the future, after or before the collision. And then the loops that you see here, so depending on the order, you see the number of loops changes, 0, 1, and 2 loops. This is the lines that are inside these loops. They have to do with the unobserved particles, the virtual particles that we never get to pick. And because this is the quantum world, we have to, therefore also integrate over the momentum of these virtual particles. I have here a one loop example, one integral, and you see I have to sum over this momentum, independent momentum of the single loop. And so the issue here is, even though we can, let's say, generate all the diagrams, computing them, finding the answer of these integrals is in principle very hard to do. These generically diverge, and even if one is able to tame, to control these divergences, the classes of functions that they evaluate to, they are unknown beyond one loop. So we are very far from understanding all but, let's say, just the first quantum correction beyond the classical term that corresponds to the tree level. And of course, the pertinence of this question is also motivated by the fact that there are large collaborations in the world, and theorists are working very hard to prepare for the, as I said, high luminosity LHC and produce theory input for it. And so this brings me to my talk. I will aim to address this difficulty of computing these Feynman integrals and obtain predictions for scattering amplitudes by exploring the potential of certain beautiful mathematical objects known as cluster algebras, how they can help us compute scattering amplitudes, particularly in quantum chromodynamics, the theory of the strong force that I had in the first slide. And this is motivated by the pivotal role that these objects have in the simplest cousin of QCD, known as Maxwell supersymmetric Young-Mills theory. Hopefully, the fact that these objects are beautiful is also conveyed in this diagram. And what I will show you in the rest of my talk will be that cluster algebras first underlie the analytic structure of known scattering amplitudes, in particular Higgs plus jet QCD amplitudes at 2 and 3 loops. So precisely for the sample event that I had in my introductory slide. So this is encouraging because it's a case study. It shows that cluster algebras might be relevant in QCD. And then the second, the main part of my, second, let's say, yes, more a newer part of my talk, I will tell you how cluster algebras allow you also to predict, to make new predictions for the first time, not just rediscard them, in known calculations, but really make predictions for 6.1 mass processes, such as the production of a massive W or Z boson together with 3 jets. For example, these quarks and another gluon. So this is the big picture for where we are heading. And this is, I think, a good time also to pause and see if there are any questions about this, the overview, the extended abstract of my talk.
It seems that there's no questions, Professor.
Okay, that's fine. I should also add, don't hesitate to interrupt at any point. You don't have to raise your hand virtually and so on. If something is unclear and you would like to understand it, please just unmute yourself and ask right away, okay? All right, so sounds good. All right, then let me start. So this is the outline. I will go on with the introduction by first telling you what cluster algebras are, since they are also in the title and they play a prominent role in the talk. And then I will move on to explain the different lines of work in part A and part B of my talk before concluding. So cluster algebras are, yes, objects that were defined by 2 prominent mathematicians, Fomin and Zelevinsky. And they are very simple at the deep down. So what they consist is a set of cluster variables. I denote these with I, the index I. And these are grouped into clusters, hence the name cluster algebra. So we take together D of these variables and we group them in this cluster. And all the clusters have the same size or rank D. So this is the rank of the cluster algebra. And these are constructed recursively, this cluster, by an initial cluster, by a procedure called a mutation. So this is, if you wish, cluster algebras are like chess. You put your pawns in the table, and that would be the initial cluster. And then the mutation is like the rule of the game that allows you to move the pawn and create the remaining clusters. And I will illustrate all these essential features in the example of the rank 2 cluster algebras, some of the simplest cases. So the cluster coordinates, they are labeled by just one integer m, 1, 2, 3, 4, and so on. And the initial cluster, since it's a rank 2, it just consists of two variables, a1 and a2. And the remaining clusters are then a2 and a3, a3 and a4, and so on. And then the mutation operation takes this simple form. If I have, let's say, yes, if I focus, okay, this L over here in the mutation simultaneously describes all three rank 2 cases. When L equals 1, we are talking about the A2, if L equals 2, about the C2, and then L equals 2, the G2. Let's focus on the C2, for example. And then if I have that M equals to 2, then I apply this relation, and A3 is given by this formula. So this is how the third cluster variable looks like, by just this mutation rule. Then if I want to produce A4, this is applying this formula for M3 odd, 1 plus A3 over A2. This is what I have written over here. And since we know A3, we can also replace it, and we find a rational expression in the variables of the initial cluster. And this goes on. You see all of these variables are rational, functions of the initial cluster variables. And something interesting happens after a certain amount of mutations. I come back to where I started. There are some non-trivial cancellations between numerator and denominator, and A7 turns out to be exactly A1. So I have a finite number of variables, and in the end, a finite number of clusters. And I can also visualize this by a so-called exchange graph, where a vertex is a cluster. So this is the initial cluster. And then a mutation is an edge. So I mutate A1, I go to the cluster A2, A3. So this is, A2, and this is A3. I mutate again, I go to the cluster A3 and A4, and so on until I'm back. And you see I have this circle topology, or this hexagon over here that you see. So any questions about cluster algebras? So in essence, as you see, they are very simple objects, and it could be given also to a high school kid to play around and produce, at least in this example, all the variables and all the clusters. So let me now tell you how they come into play. They appear prominently in many areas of theoretical physics, and I just mention a few. I won't go into lots of detail, but these are some of the first appearance of cluster algebras in theoretical physics. But in particular, what interests me, what was motivation for me and my collaborators, was that in this very simple cousin of QCD called maximal supersymmetric Mills, these cluster algebras were observed to govern the kinematic singularities of scattering amplitudes. So kinematic singularities means where scattering amplitudes become divergent as functions of their kinematic variables. So let's say the momenta of the external particles, the masses of the internal propagators, and so on. And maybe, okay, it's a curiosity. What does this buy me? The highlight of this, the importance of these kinematic singularities is that, or of cluster algebras that they provide them, is that they also allow one to compute the amplitudes themselves by this amplitude bootstrap procedure, which is just, I visually illustrated to just give you the basic idea. Instead of computing all these Feynman diagrams that are many, many and very hard, one can produce a finite number of candidate amplitudes at each loop order based on this information on the kinematic singularities. And so these are the like balls that you see over here. So 7, let's say, possibilities, 7 candidate functions at a given loop order. And then it's possible with certain additional information to identify which of those like possibilities is the actual amplitude. So this very interesting method was pioneered by Dixon and collaborators. I also worked myself on this for several years, and it's also reviewed in this article by the collaboration of the scattering amplitudes from geometry to experiment. That I guess was one of the reasons why I was invited. This article was what spurred interest in some of your group members. And it's a very active area of research, this amplitude bootstrap, with papers appearing as recently as last week, let's say, on the subject. But okay, this is an aside. The important thing is that cluster algebras really allow us to obtain full amplitudes in the end with minimal additional information, at least in this cousin of QCD. So maybe they help us also in QCD in making predictions for experiments for the LHC. And this brings me to the first part of the first part of my talk beyond the introduction. So in the past, there has been a very rich history of knowledge transfers from this cousin of QCD to the actual theory and to, yes, phenomenological calculations relevant for experiment. And some examples is generalized unitarity method that is essentially allowed the calculation of all one-loop amplitudes in massless gauge theories, in any gauge theory, and so revolutionized the first quantum correction. And then also more recently, the method of canonical differential equations, to which I will return to in a next slide, but this also came essentially from the realm of this very simple model. So it's natural to ask, because of this very successful history, could also cluster algebras that appear in this model theory, could they also have a large impact in QCD? And this was the motivating question in my paper with, yes, Dima Chicherin, Johannes Hen. And to answer it, for generality, we searched it in individuals Feynman integrals or to collections, to families thereof. And in particular, we started with those that have massless internal propagators and in dimensional regularization. I will explain these terms a little bit. Scalar means that they have no tensor structures, they say no Lorentz tensors or spinors. And this is because these tensors we can always reduce to scalar integrals due to the work of initially Passarino and Velkman, more recently to Tarasov. So this is no loss of generality. This in a sense is known or done. And then I will also go to dimensional regularization, meaning that the dimension of loop integration will not be integer, will not be the space-time dimensions we all live in, but we will go slightly away from it. This allows us to regulate this divergence of the integrals. And then only at the very end, when we have summed everything up, we take epsilon at the very end to get finite quantities and meaningful quantities. And then finally, massless propagators, because they are a simple starting point and it connects well also with this model theory that also has massless particle content. And finally, yes, I should also mention that it's a well-known fact, okay, it's more than 45 years or so old, that not all scalar integrals are linearly independent. They obey this integration by parts identities when one differentiates, with respect to some of the kinematic variables, and then one obtains more integrals in this same set. And so not all, we call a basis in this vector space a minimal set of linearly independent integrals. We call them master integrals, and we can also group them in this vector F. That I will talk about also in the next slide. So how do we actually compute these integrals, which also will allow me to make contact with cluster algebras? This method of canonical differential equations. So since we have a basis, it's no wonder that if I differentiate with respect to the basis elements, I land back into the basis. That's what, in essence, this equation first tells us. So this is the total differential, namely the partial derivatives with respect to the independent variables times the differentials of these variables. And then, okay, I also need a matrix. I have a vector here, I have a vector here. I also need to dot it with a vector that tells me how exactly the derivative of each vector maps back to the basis. And what canonical means is that this dependence on the dimensional regulator is upfront. Normally, this whole matrix would also depend on epsilon, but the fact that we can factorize it, this is the canonical part of these differential equations, and this is what really greatly facilitate the solution of the calculation of the integrals at each order in epsilon. It neatly separates the order of epsilon that we are computing these integrals in. And for the y class of integrals, so-called belonging in the polylogarithmic functions, which will be the focus of this talk, this particular matrix has a constant matrix part. So this is just numbers, a constant matrix. And then it also contains logarithms of certain algebraic functions of the kinematic variable. So all the kinematic variables of this matrix hides in these objects, which are called symbol letters. And as you see, they capture the singularities of these integrals and therefore of the amplitudes, because if alpha, if this letter goes to 0 or infinity, you see that also the logarithm diverges. So therefore the integral itself diverges. So that's why it's in this sense that these letters are tied to the singularities of integrals and amplitudes. And in n equals 4, it's these that are related to the cluster variables of cluster algebras. So this is the only, let's say, relatively heavy technical slide of my talk. Please keep in mind that these are the objects of our attention. In a sense, from all the differential equations, what we will keep are these letters. These are the most complicated parts, as the rest are just vectors and constant matrices. And this is where cluster algebras come into play in n equals 4, and as we'll see also in QCD. And maybe very briefly, also certain products of these constant matrices that vanish are also important because they provide analytic information. But okay, at the level of this talk, I don't think I need to go any further unless there are questions about it. But okay, this is also a secondary information to record from this equation apart from these letters. So let's go to the first example that we discovered where cluster algebras underlie the analytic structure of QCD integrals and scattering amplitudes. And this pertains in particular to 4-point integrals with one leg of shell, meaning all the remaining legs, their square momenta are null, and only for this one it's not null. Or if you wish, massless particles. 3 of the external particles are massless. And the kinematic variables in this setup, it's 2 of them. It's these products of these. So if the squares vanish, one should also only consider products of these massless momenta. And we don't have to consider P1 dot P3 because there is momentum conservation and it's related to Z1 and Z2. And so these are some particular, let's say, integrals that have these kinematics, 4-point with one off-shell or massive leg. And the alphabet with this sense over here of these integrals is known because it has been, these integrals have been computed long time ago. And you see in this example, the very simple functions of the kinematic variables, the linear functions of the kinematic variables. And these, like master integrals, they basically describe all Higgs plus jet production amplitudes, where this is the Higgs particle, the massive particles, and then this is the extra jet, and these are the, let's say, the incoming particles, the proton constituents, the gluons or the quarks that are in parts of the proton. So these are contributions indeed to the Higgs plus jet production amplitude in the heavy top limit. It means that we are considering the top mass to be very, very heavy, which is a very reasonable approximation to do. In my work with Chicherin and Hen, we discovered in the first instance of cluster algebras in QCD amplitudes. In particular, we demonstrated that this alphabet is equivalent to the set of cluster variables of the C2 cluster algebra, the one that I introduced cluster algebras with. So these 6 variables are in fact the letters of the Higgs plus jet amplitude, the symbol letters of the Higgs plus jet amplitude, if one finds a particular mapping between the kinematic variables over here, the momenta, and the variables of the initial cluster, A1 and A2, on which all other cluster variables depend. So this was very, very exciting for us. It opened the door to possible applications of cluster algebras to particle phenomenology. And we were very excited until Morrison's work led to a conundrum or a fly in the ointment or a conflict or a contradiction. Namely, the work of my collaborator, Johannes Hen, in later work, went on to compute certain 3-loop contributions, again to the same process. So you see 1, 2, and 3 loops over here, this non-planar 3-loop box. And they realized that, okay, some other 3-loop contributions, they still are described by the C2 cluster algebra. They still have the same 6 letters. But this particular 3-loop non-planar box also has an extra 2 letters. So the C2 cluster algebra is simply too small to describe the 3-loop alphabet of this Higgs plus jet amplitude. So what shall we do? Should we just give up? Was it just a coincidence? Was it an accident that 2 loops that cluster algebras play a role, or are they more fundamental? And to try to answer this question with my students, Georgios and I, we first had the idea that, okay, finite cluster algebras are in fact in one-to-one correspondence with Lie algebras. And therefore, they are described by Dinking diagrams that hopefully you know from your group theory courses and your favorite phenomenology and model building and so on, about the gauge groups. So there are, of course, certain generic series, and then there are some exceptional cases. I guess there should be E8 also over here that I forgot to add. But in any case, if yes, we are thinking about so the rank, as we said, is the number of variables. In this example, we have 2 variables, so we better look for a rank 2 cluster algebra. And therefore, we should restrict to A2, C2, and G2 if we are to find another cluster algebra that describes then the 3-loop, this 3-loop contribution. And then we can also count the number of cluster variables. And for A2, it's 5 of them. In fact, this coincides with the 1-loop diagrams for this process. And then C2 we know already, it has 6 variables. And very interestingly, G2 has exactly 8 variables. So the number coincides with the number of letters of this new 3-loop contribution. So we suspected that what happens is that 3 loops the C2 cluster algebra is enlarged to this G2. And we wanted to prove this, if this is the case. And in order to do this, we had to somehow prove that this alphabet is equivalent to the alphabet of the variables of the G2 cluster algebra. And this, yes, we had to think a little bit more about what equivalence of alphabets means. And this is, if you wish, a linear transformation of these logarithms of the letters that is invertible, so non-singular transformation, that therefore maps a set of letters to the logs of the letters to a linear combination of other logs of letters. And so in this example, we also need to change variables, of course. Here we have the Z1 and Z2, whereas in the cluster world, we have the variables of the cluster variable of the cluster algebra, so A1 and A2. So we need to find some transformation to also make this contact. And okay, I don't want to perhaps tire you with this. The main idea is that if the variable is itself a letter, then there are enumeratively many different dials, or let's say numbers that we can change to find the solution. So it's not completely arbitrary. There exists a number of, let's say, integers that we need to play to test, let's say, that this n is equal to 1 or 2 or 3 and so on. So essentially what we can do is we can try test values for these, let's say, pre-parameters of the transformation and see if it works. And this is what we tried. We chose very simple values for these parameters, and we indeed succeeded. So we proved that if one similarly transforms the kinematic variables of the process, what is here, yes, this, if you wish, rescaled Mandelstam variables of the process to the variables of the initial cluster, the initial cluster of the G2 cluster, A1 and A2, then one precisely finds this equivalence, that the new 8-letter alphabet that starts contributing at 3 loops is equivalent to the G2 cluster algebra. And I find it extraordinary, the pattern that emerges, namely that this factor L that showed up in the mutation relation of rank 2 cluster algebras is really the loop order. At loop 1, yes, one loop, you have the A2 cluster algebra, which in which the mutation here has L equals 1. And then the 2-loop example gives a C2 cluster algebra. The 3-loop example gives a G2 cluster algebra. So this clearly cannot be an accident. It's far too suggestive, this process, at least in my mind, that cluster algebras are here to stay, and they might really simplify future collider calculations. So are there any questions? Because I'm very close to finishing the first part of my talk.
I have one. Can you hear me?
Yes, go ahead.
Sorry, I didn't catch at all. What is the importance of cluster algebras? Could you summarize?
Yes.
Is for you have a better control of amplitudes, or it's
so F is the set of master integrals of let's say given amplitude, all the linearly independent integrals that contribute to an amplitude. And the most complicated part of these integrals are these letters. These are some algebraic functions of the kinematic variables of the process, and finding them is very, very hard. And therefore also computing the integrals and therefore computing the scattering amplitude is very hard. And what I am showing here is that cluster algebras allow you to find these letters of the integrals and of the scattering amplitudes, of QCD amplitudes. Does this answer your question?
Yes, yes. But it's for loops or only for loops?
So in this particular example that I'm talking about, we have established that cluster algebras, yes, play a role at up to 3 loops, at 1, 2, and 3 loops. And this is the also current limit. This is where, calculations are done up to 3 loops at the moment.
Oh, okay, okay. But this is also including massive particles or works only for massless?
This is a massive external particle. Do you mean massive propagators?
Yes.
Massive propagators, to the best of my knowledge, yes, this has not been examined yet.
Okay. Okay, thank you.
You're welcome. This would be a next step, of course, going to the case of massive internal propagators. But certainly for a huge range of phenomena, as I said, the Higgs plus Z production and the heavy top limit, we can content ourselves to massless internal particles. It's a good enough approximation. Also, as I was saying, for massive vector boson production, again, the internal particles can be assumed to be massless. So I will also skip maybe this additional information about this relation between matrices, constant matrices that show up in the differential equations of master integrals. But we indeed observe some that had not been observed before, and they were verified in actual 3 loops planar Higgs amplitude in consequent work. So we did teach the phenomenologists something that they didn't know, for example. And yes, I will, unless there are questions, I will skip to this part. Perhaps it's a bit technical for this audience, but if there are questions, I'm happy to return to this at the very end. But apart from the letter, we also revealed some additional informations that phenomenologists didn't know about 3 loops Higgs amplitudes. So this brings me to the second part of my talk. Up to now, I told you about rediscovering, let's say, that cluster algebras are behind existing QCD results. So the amplitudes of Feynman or master integrals I talked about were known, yes, before our work, before cluster algebras were even introduced. But certainly our discovery paves the way for actually applying cluster algebraic methods to make new predictions. And so this was the main topic of the second part of my talk. Can we use cluster algebras to make new predictions? And the strategy I will follow in the second part of the talk is to harness as much information from this cousin of QCD, this symmetric cousin of QCD, as much as possible. So The main property I will use of this cousin of QCD is an additional symmetry that this has. This goes by the name of dual conformal invariance. Conformal invariance is the invariance under scale transformation. So you can also change the distances between things. So these are transformations that preserve angles between things, but they can deform things otherwise and make them bigger or smaller. And so it has been observed, and there is lots of evidence that normalized amplitudes, appropriately normalized amplitudes in this model theory, and also Feynman integrals that they contribute to them, are invariant under conformal transformations of these x variables. So these x variables are defined such that their differences are equal to the momenta of the scattered particle. So let's say x2 minus x1 equals p1, the first momentum of scattering process. And these are cyclically identified. So if I have 6 particles, x7 will be equal to x1. So I will just illustrate these main features in this well-known example of the one-loop 4-mass box. So again, all propagators are massless, and then all the external legs are massive. And here I will denote a massive leg by a pair of massless legs. This is possible because, okay, if I take 2 massless momenta and I take their sum, I generically have a momentum that is massive. The square of this is no longer 0. So I can describe massive momenta as a pair of massive momenta simply to make contact with the fact that this model theory only has massless fields in its Lagrangian. So the point is that because we have this conformal transformation of the x's, so these x's, if you want, they are also Mandelstam invariants. You see they are sums of momenta squared. So this process, if we just had Lorentz invariant, it would depend on 6 variables. This Mandelstam variables. So you see 1, 3, 1, 5, 3, 5, 3, 7, 5, 7. But it turns out that instead of these 6, this integral only depends on 2 variables, and these are the conformal cross ratios. So these are combinations of the Lorentz invariant that are also invariant under conformal transformations. You see that if I scale all the x's with a, let's say, scale a factor lambda, these also remain scaleless. They don't scale. So these are conformal invariant quantities, and this integral does depend on simply 2 instead of 6. 2 conformal invariant quantities rather than 6 Lorentz invariant quantities. This has been really established if one really looks at this integral. And if you want, this is how this integral looks like very explicitly. It's not important what follows, but just to show you that this is no like abstract quantity, it's just some combination of dilogarithms and logarithms. So very, very concrete function. So the main idea now that I will use to make new predictions is the fact that if we have any integral that has this dual conformal symmetry, I can just pick a frame where, let's say, one of these dual position variables goes to infinity. And see, these are the cross ratios u and v that I also had in my previous slide. What happens if I take x7 to, is there a question?
No.
Okay. So just really, let's take x7 to infinity. Then this x squared will also go to infinity, and so will this one at the same rate. So in the limit, we'll have something which no longer looks conformal invariant, and is just a ratio of the momenta of the particle. So x1, x3 is just the momentum of this particle, which I called k1, and then x1, x5 is the momentum of these two particles, so k1 and k2, and similarly for v. And because this x goes to infinity, we no longer see it. If we are, yes, in this particular frame, this x is very far away from us. We don't see it. And then for this like 4-point integral with dual conformal invariance becomes a usual Lorentz invariant triangle integral. So this is something that was known long time ago, but perhaps it wasn't, its power was not appreciated because it does not really apply just to this integral. It applies to any n-point dual conformal integral, and it relates it to an n-1 point Lorentz invariant integral and at any given loop order. This is a symmetry argument, really. I illustrated it in a one-loop example, but this is just a consequence of symmetry. The function is the same, as you see, for these two integrals, and what changes is just their variables, how their variables, what the values that their variables take in the DCI or the Lorentz invariant case. So this is the main idea I will employ. So maybe I should pause again to see if there are any questions about this.
Everything is fine. Thank you.
Okay, hopefully I didn't lose you. So let's apply this method. Of course, if the functions themselves are equal between an integral contributing in this model theory and an integral that is Lorentz invariant that we know and understand and we are more familiar with, the same should hold also for their letters. If the functions are the same, the letters or the alphabet, the symbol letter should also be the same. And then, of course, this does not just hold for individual integrals, but also to collections of integrals. The alphabet, the sum of all the collection of all the letters, if you take a collection of integrals, so the alphabet of the union of integrals will be the union of the alphabets of each individual integral. And here I will apply it to a particular collection of integrals, those that contribute to the 9-particle alphabet, 9-particle amplitude in n equals 4 super Young-Mills theory. So this is work that I did with my first PhD student, and it's based again on cluster algebras. And so the additional information I will also use is that, okay, this is 9-particle massless scattering in n equals 4 in this simple model of a gauge theory. But the alphabet of 9-particle massless scattering also includes the alphabet of scattering of fewer particles, or I should say, yes, if an integral with nice massless external legs, a master integral family that in its top sector contains an integral topology with 9 legs also contains subintegrals where some of the propagators have been shrunk. This is a consequence of the integration by part relations that you can also produce from it the so-called subtopologies of integration by parts, the integrals where you have also contracted some of these propagators. So if I contract, let's say, this propagator, I produce a massive leg. And then if I contract another propagator, I produce another massive leg. So also integrals that have fewer legs, and some of them are massive, are also contained in this family. And then for this alphabet of 9-particle massless scattering will also contain, let's say, the alphabet of 5.2 mass scattering of this sort. So I will focus in particular on these sub-alphabets. I will focus on this 7.2 mass scattering integrals in dual conformal integrals, or this sub-alphabet of the 9-particle alphabet in n equals 4 that has this dual conformal symmetry. And I will do the same process. I will take one variable to infinity, break this dual conformal invariance, and therefore in this way I will obtain predictions for letters of 6.1 mass processes. This look like one loop like integrals, but these are for illustration purposes. I could also have a 2-loop integral and the same kind of limit would apply. And indeed, here I have, let's say, 2-loop letters for 9-particle scattering, and they will reduce to also 2-loop letters for 6.1 mass scattering. Which is a state of the art. It has not yet been calculated by conventional means. And then if I want, I can also take the limit of this leg becoming massless and also produce letters for massless scattering. And this is the state of the art. There was recent work by Hen et al. And Abreu et al. Computing Feynman integrals that are 2-loop and 6-point massless. So here I will also do a check of the new result, the new predictions we obtain. And then I will also find some other sub-kinematics or sub-alphabet of the 9-particle massless alphabet. This is a hexagon with 3 massive legs, and this will allow me to produce 5.2 mass, the letters of 5.2 mass processes in QCD, which are also at the state of the art. So maybe I can also speed up a little bit because I see that I am running out of time. These are certain structural information about our starting point. This alphabet for 9 particles scattering in the cousin of QCD has a huge number of rational and square root letters that have this the square root letters have this particular numerator versus denominator form, and so if we do this, if we find the sub-alphabet that relates to 6.1 mass kinematics, these reduce in numbers, and we can further single out those that are not letters of further subkinematics, so further integrals with fewer legs, where we have further shrunk some more propagators. And in any case, all these are new predictions because no one has been able to compute 6.1 mass integrals at 2 loops. And we find interestingly that those that have that contain square roots have this very novel feature. They contain nested square roots. You see, there is a square root of a square root. So this is more complicated than the so-called vanilla form of letters that had appeared so far in all other processes in QCD were terms here and here were polynomial or rational functions in the Mandelstam variables. So this is a completely new feature that we find, and it had only been appeared in calculations of Feynman integrals with massive propagators that evaluate to more complicated functions. So we are talking about integrals that also contain the elliptic generalizations of these polylogarithmic functions. So it wasn't clear if these letters play a role if one restricts to purely polylogarithmic functions. So our results for the first time illustrate that this type of more complicated letters are ubiquitous in quantum field theory, even if we just restrict to massless propagators and to terms purely expressible in terms of these polylogarithmic functions. So in any case, we make a definite prediction, and we are confident that our results will help also to the calculation, will aid the calculation of this 6.1 mass master integrals for, let's say, as I said, W boson plus 3Z production at the LHC. I will also speed up here, but I mentioned if we have this alphabet, we can also take a massless limit, and then we can compare with the recent work of these groups, late 2024 and early 2025, where they computed this 6.2 loop planar master integrals. And we find that essentially all these letters in our limit are contained in our prediction. So I find this a very, very encouraging consistency check of our prediction. And we also find new letters, I should say, also in these kinematics that might appear at higher loops, so at, let's say, 3 loops in this process. Similarly, we can also find predictions for 5.2 mass processes in QCD. There are some, again, novel features. We don't find a complete overlap in this case. There are letters in these calculations which we miss, but we nevertheless also provide some letters that are not contained in these calculations. So maybe this will also appear at higher loop. It's, I think, quite promising. So this brings me to my conclusion, because I don't want to take a lot of your time. I hope I convinced you that these beautiful mathematical objects underlie the analytic structures of many physically relevant Feynman integrals and scattering amplitudes. I first went from discovery, from looking for cluster algebra structure in QCD, and I found it in 2 and 3 loop contributions to Higgs plus Z amplitudes, and then also applied it to make new predictions for 5 and 6 point processes in QCD, which is the current state of the art, at least in the high multiplicity frontier. And so, for example, we expect that our letters will contribute to the calculation of 2 loop master integrals for yes, this 6.1 mass process that I illustrate here. And there are many, many also interesting questions to address in the future. Thank you very much for your attention.
Thank you so much, Professor Georgios. We have time, if you don't mind, for questions.
No, that's fine.
To the audience. Okay, perfect. So please, guys, raise your hand and open your microphone in order to have the questions. Go ahead, Jorge, please.
Hello, do you hear me?
Yes, hi, Jorge.
Hello. I have 2 questions. The first one is, does cluster algebras could help with more massive external particles? I mean, I think that you mentioned that the next case of study is with two massive external particles, but I wonder if you can use more massive external particles.
Yes, the answer is yes. So to your first question, we would have to, if you wish, the structure that you see here, maybe here. Yes, if I have n massless, if I have the alphabet of n particle amplitude in this model theory, I can also find alphabets for yes, processes with n minus I legs, out of which I are massless. So, for example, 8.1 mass, 7.2 mass, or 6.3 mass over here. In dual yes, if you think about, yes, dual conformal invariant quantities, and then, as I told you, okay, so from this 9 particle alphabet, I arrived at 6.1 mass prediction and 5.2 mass. If I go, so the short question, sorry, is if I also compute the 10 particle alphabet in this theory, I will be able to compute 6.2 mass processes, so more external massive legs, and 5.3 mass processes in QCD. And so I just need to continue computing, yes, amplitudes with a higher number of particles in this model theory, and then I anticipate that cluster algebras will also be able to therefore describe indeed 6-point and 5-point processes with more external massive particles. So hopefully I did not lose you, Jorge.
Okay, thanks. I think I got the idea. The other question is about twistor geometry.
Mm-hmm.
Well, I was wondering if there is a connection between twistor geometry and these cluster algebras.
Absolutely, absolutely. So I deliberately refrained from using twistors just to not confuse anyone more, like, because these are, let's say, more technical knowledge that not anyone has. But so if, to summarize for everyone, if we are talking about theories with dual conformal invariants, then there is a more natural set of coordinates than momenta. So instead of having momenta, you can use these alternative coordinates called, yes, twistors, or momentum twistors in particular. And these are simple because they are unconstrained. Let's say the momenta, they all sum to 0. So only n minus 1 of them are independent. And so also if you have some of the square momenta to be 0, they have some, redundancy and so on. These like momentum twistor variables are completely unconstrained, and that's their benefit. So the connection with cluster algebras is because this momentum twistor space, for an n scattering process in this model theory, has the structure of a 4,n Grassmannian. So the twistor, momentum twistor geometry is related to this object, which is the 4,n Grassmannian, the collection of 4-dimensional vectors in 9-dimensional space or n-dimensional space. Cluster algebras also provide good coordinate frames, good coordinates for the geometric space. So that's how the connection between cluster algebras and twistor geometry, that's how the two connect.
Thanks, and that was a very good talk.
Glad you liked it, Jorge.
Okay, thank you. More questions, guys? No more questions?
Well, maybe it was a bit heavy as a talk. It's true that I prepared it for a more specialist audience last week, and yeah, I didn't have time to, or yeah, I didn't think about making it simpler, to be honest. But perhaps, yeah, there was a lot of technicality in it in the end.
Okay, well, it seems that there's no more questions, so we thank again to you, Professor Georgios, for this amazing talk, and we hope that we can have you another time to another amazing talk like this. So
Absolutely. I again, I'm very grateful for the invitation, and yeah, hopefully we meet again in person next time.
we hope have the opportunity. So see you. Have a good night.
You too. Have a nice day. Bye bye.
Bye.